Hi guys, I'm Lauren Smith and I'm studying theoretical physics in Trinity. I'll be taking you through 2020's higher level question 10 today. Now this question is split into two parts. You choose one in accordance with the optional topic you've chosen. Question 10a is for those who study particle physics and question 10b is for those who study applied electricity. So let's go. Okay, so here's the first look at our question 10 and I'm going to start with part A, which focuses on the option for particle physics. Now, in part A, we are told about the DUNE, or the Deep Underground Neutrino Experiment, and work of which was done in Fermilab starting in 2017. Now, we are told that protons will be accelerated to hit a fixed target. They will produce pions and kaons, which will then decay and transform into an intense beam of neutrinos. These neutrinos will then travel at 99% of the speed of light, or 0.99 times the speed of light, through the Earth, and they say that no tunnel is required, and it goes from Fermilab all the way over here to the Sanford Lab in South Dakota. We are told here in this diagram that the distance between these two labs, or the distance in which the neutrinos travel, is 1,300 kilometers. And this information leads us into answering parts 1 all the way down. And in part 1, we are asked, what are the two fundamental forces that the neutrino experiences? Okay, so how do we decipher this? Well, we know the neutrino is a lepton. It has no charge and it interacts weakly with matter. With these few bits and pieces that we know of the neutrino, we can then hazard a guess as to what the answer may be, which is that it experiences the weak nuclear force and the gravitational force. It experiences the two weakest forces of the four fundamental forces, which are these two. Now, it doesn't make sense for the neutrino to experience, say, the electromagnetic force, since they have no charge. Since the strong force binds quarks together and the neutrino is not composed of quarks because it's a lepton, neither is it a quark. Therefore, it's a bit nonsensical for it to experience the strong force. Therefore, we're left with these two options. If you don't know these options off the top of your head, look at the characteristics, the properties, the key qualities of the neutrino and try and logic your way into an answer. You'll get 3 marks for each correct force, giving you 6 in total. In part 2, we are told that pions and kaons are members of the meson family. And then we are asked, what are mesons? Now, with this question, what we would like in the answer, what the marking scheme would like you to put down, is that how would you distinguish these meson particles from, say, other particles? What is characteristic to these particles that are not characteristic to, say, the baryons or so forth? Well, here's the answer. We know that mesons are indeed subatomic particles, but they are also composed of a quark and an antiquark, and that is key to the definition of the meson. Your key phrase here is that it is composed of a quark and an antiquark, and that will get you 3 marks. Okay, before moving on to part 3, I just want to draw your attention to page 48 in the Formula and Tables book. In particular, we're going to be looking at the lepton class of particles, and we are going to be looking at the masses of the electron neutrino, the muon neutrino, and the tau neutrino in particular. Just to point out that these masses listed in this table for all the particles shown on page 48 are relative to the mass of the electron. In part 3, we're asked to list the 3 types of neutrino in order of increasing mass. You can find all of these neutrino types in the Formula and Tables book along with their masses. If you're asked any question like this in the exam, now you can find all of these types of neutrinos in the Formula and Tables book on the page we just looked at. And we can also find their masses. So it does not make any sense for you to learn off the masses. I would advise against this. You're just wasting your time and energy. It's all in the Formula and Tables book. And even if they only give a rough approximation, that will do you in the exam. You are not expected to learn these tiny, tiny figures off. With that being said, I'm going to give you the list. The 3 types of neutrinos, which you can see in the Formula and Tables book, are the electron neutrino, the muon neutrino, and the tau neutrino. Now, you'll get 2 marks per correct neutrino, okay, which you can directly copy from the formula tables book, giving you 6 out of 6. It does say in the question that you need to list them in order of increasing mass. However, this does not make sense. If you even look at the page in the formula tables book, you can see that it looks like all the masses are given the same definition, that they are under 4 times 10 to the power of minus 6 of that of the electron mass. So in terms of looking at them in the formula tables book, it seems as if they all have the same relative mass to the electron, or the approximate mass. So therefore, in the marking scheme, they have specified that any order is accepted. This was an error. In part 4, we're asked, why is no tunnel required to transport the neutrinos underground to South Dakota? This was mentioned in the blurb of information we were given before the questions. So why is this? If you are stuck on this question, because it isn't something that you would necessarily learn off, you're going to be tested here on your knowledge of the neutrino. You have to reason out this answer for yourself. Think of the qualities and the characteristics of the neutrino, and why would no tunnel be required? What qualities must, say, a particle or a subatomic particle have in order for a tunnel to be necessary, per se? These are the questions you need to be thinking during the exam. It's very helpful as well. You can really reason them out by yourself. And I can give you 3 answers, all of which are accepted in the marking scheme. No tunnel is required to transport the neutrinos since option 1 is that their mass is quite small, even negligible in fact. They are even sometimes known in particle physics as ghost particles, that they can really pass right through matter. And this can be synonymously stated is that they have little interaction with matter, as is the 3rd option down here. And this can be reasoned because they have little interaction with matter, since they are not dictated to by the strong force, and therefore they interact weakly with matter. And this can also be synonymously stated in that they have no charge. They are unaffected against charged matter. They're not swayed by charged matter. They, again, are not dictated by the electromagnetic force, as we saw in part 1 as well. If you say either of these 3 options, then you will get the required 3 marks for the question. In part 5, we're asked to calculate the time taken for the neutrino to travel from Fermilab to South Dakota. Now we want the time, we have the distance, and we have the speed. In order to calculate the speed fully, I would like to draw your attention to page 47 of the formula tables book, in which we will be looking at the variable c, which is the speed of light in a vacuum, which we're going to approximate to roughly 3 times 10 to the power of 8 meters per second. For this question, we're going to need the formula v is equal to s over t, where v is the velocity, s is the displacement the particle travels, and t is the time taken for the neutrino to travel the distance required. Now, this formula isn't strictly in the formula tables book. You can derive it from the kinematic equations on page 50. However, it is extremely handy to have this formula in your head. You'll even need it in some questions in the mathematics paper, whether you're sitting higher or ordinary level maths. You will require this formula. So it is best to learn it off. And just even putting it down, as I would recommend you to do all your formulas, whether they're in the formula tables book or not, is to put them down, since you will get automatically half of the marks you need for this question. So you'll pick up the majority of the marks. Okay, so we know that the distance, s, is equal to 1,300 kilometers, which is just equal to 1,300,000 meters. We're going from one unit, which is distance and speed, to another unit, which for time, which is the second. So we're going to have to convert this into SI units. The other variable which we need in order to calculate the time is, of course, v, the velocity, and that's equal to 0.99 times the speed of light. Now, we were told in the formula tables book, well, we're going to approximate it to one significant figure, that the speed of light is 3 times 10 to the power of 8 meters per second. Multiplying this by 0.99, easy calculation, we're going to get 2.97 times 10 to the power of 8 meters per second. Okay, so we have all the variables we need. Our target variable is t, so it is optimal to manipulate the above formula in order to get t on its own. So all we need to do is substitute in the figures for displacement and velocity and get our answer. In doing so, that we get that time is displacement s over velocity. Substituting in our figures, we don't get any extra marks for doing this in this part 5 here. However, it is always a very good idea in physics to put down all of your rough work, because in some questions in the marking scheme, they will give you marks for just even substituting in the figures into the formula. So always keep that in mind. Okay, so let's put this into our calculator. We have 1,300,000 meters. Be careful with how many zeros you put in. And that's all the way over 2.97 times 10 to the power of 8 meters per second. Hitting that equal sign, we're going to get 4.4 times 10 to the power of minus 3 seconds. However, this can be rounded because times 10 to the power of 3 can be substituted by the prefix m, which means milli. And we can round 4.377, which we saw earlier, to 4.4. It's just tidying up the answer here. Giving the answer like this, or even the answer in the calculator, but make sure you round. They don't want loads of decimal places in your answer. They want you to tidy it up a little bit. So doing this would be just fine, or even to 2 decimal places will get you 3 marks, giving you 6 out of 6. Okay, we're going down to our original question again, and we are told that in another experiment in Fermilab, 2 protons, each with a kinetic energy of 29 giga electron volts, collide and new particles are created. After the collision, the total kinetic energy of the 2 protons and the new particles is 16 giga electron volts. And with this information, I'm going to turn over to question 10, part 6. But before I do that, we're going to need a couple of pages in the Formula and Tables book in order to answer this question. First of all, we're going to need page 45 because we will need the factor, which represents the prefix giga. We're going to need page 46 for the value of the electron volt. We're going to need page 47 as well for the speed of light, which we had in a previous question. And finally, we're going to need page 55 as well for the mass energy equivalence formula, E equals mc squared. And finally, in part 6, we're asked to calculate the total mass of the new particles created. Now, we are told the kinetic energy beforehand was equal to 29 giga electron volts times 2, because we had this amount of energy per proton, and that's just equal to 58 giga electron volts. We also know the kinetic energy, or the energy, after the collision, which is 16 giga electron volts. However, for the mass energy equivalence formula we're going to need later on, or we're going to use to calculate this total mass of the new particles created, we're going to need to find the difference in energy before and after, because this discrepancy in energy will reveal to us how much energy converted into mass. Getting the difference between these two energies, we get that the total energy difference is 42 giga electron volts. Doing this simple calculation out, you'll get 3 marks. Now, we're looking for mass, the unit of which is kilograms or kg, and therefore we must change this unit of energy over here from giga electron volts into joules, because that is the SI unit of energy. We're going to be converting from one physical quantity to another, so everything has to go into SI units. So we have 42 times 10 to the power of 9, because that is the factor which represents this prefix here, giga, as we saw in the Formula and Tables book. And we know that the electron volt is 1.6 times 10 to the power of minus 19 joules. It's okay to just round it to 2 significant figures. Let's put this into the calculator. So having it up here, since we're going to be using scientific notation, we're going to be using indices and whatnot, it is best to multiply these 2 figures using brackets. Now we have 42 times 10 to the power of 9 multiplied by 1.6 times 10 to the power of minus 19 equals 6.2 times 10 to the power of 9 joules. Giving it to 3 significant figures as shown in the calculator, not forgetting our units, just to keep track of them as we go through the question. It's always very handy. I'd put in, to whatever calculation you're doing, I'd always substitute in the units just so you can keep track of yourself, because if the answer has the correct units at the very end, then more than likely your calculation is right. So just calculating this figure here, i.e. the figure in SI units, we're going to get 3 marks, giving us 6 marks out of 12 so far. However, we are going to have to still calculate the total mass of the new particles created. Since we have a change in energy, and due to the energy conservation law, energy cannot be created nor destroyed, but it must be converted from one form into another, or converted into mass. This energy cannot be destroyed, it is converted into mass. Okay, so this change in energy is the change in mass we require, and therefore we're going to have to use the formula E is equal to mc squared. Now I use this little triangle here, it looks like a triangle, it's really the capital delta, which in science means change of or change in, and I would always submit this into the formula, into this particular formula, since we're looking at changes in energy and mass, just to keep your head in the right track. Now putting this formula down, which we saw in the formula tables book, you're going to get 3 marks. We want the change in mass, which is going to be the mass of these particles. Just manipulating this formula here because we want to get the target variable on one side and express it in terms of variables, the values of which we already know. So we have that the change in mass is equal to the change in energy over c squared, which c is the speed of light in a vacuum. Substituting these values into the formula, which I'd always recommend you to do, we just need to put them into our calculator now. For if you don't turn the calculator off or use this button here, which will reset the calculator, it will be stored as an answer. So we have 6.72 times 10 to the power of minus 9 joules, which is our answer stored here. This also is very useful to have because then you don't have to re-input the figure, which means that you're less likely to make a mistake. And this figure itself is over 3 times 10 to the power of 8 all squared. This figure in here is just the speed of light squared. Hitting that equal sign, we get our answer to be 7.47 times 10 to the power of minus 26 kilograms, roughly speaking, giving us our final 3 marks, making sure that you do not forget your units, which are kilograms. And this figure here has a slight discrepancy from the marking scheme, and I just wanted to highlight or note that such small discrepancies in these types of answers, especially in particle physics, because you're dealing with really, really tiny numbers, is acceptable. It's allowed due to we have a little bit of wiggle room here. Okay, and I suppose this leads us on to finally finishing this question, which we're going to go back to the original question 10 part A for. We are told that Enrico Fermi proposed the existence of the neutrino, and that he also built the first self-sustaining nuclear fission reactor. So we're looking at keywords like self-sustaining, nuclear fission, nuclear reactors, all of that. And this leads us nicely into answering part 7 all the way down to part 10. And in part 7 we're asked, what is nuclear fission? Simple definition here will suffice, and we can give this as follows. That nuclear fission is the splitting up of a large nucleus into 2 smaller nuclei of roughly the same size with the emission of energy and neutrons. We're going to get 3 marks for stating, say, okay, what is nuclear fission? What is it? It is the splitting up of a large nucleus. It is the splitting up of a large nucleus into 2 smaller nuclei of roughly the same size. So you'll get 3 marks for that. Plus another 3 marks for stating what does it result in. It results in the emission of energy and neutrons. And that will get you 3 marks, giving you 6 out of 6. If you say that it is the splitting up of a large atom, as opposed to the splitting up of a large nucleus, as in the definition, you will lose a mark. You will lose a mark, say, if you omit the nuclear size, in that these 2 nuclei, once this large nucleus is split, will be smaller than this nucleus. You will also lose a mark if, for any instance, you omit the fact that not only does this nuclear fission emit energy, it also emits neutrons. If you leave out those neutrons, you'll lose a mark. Okay, in part 8, we are asked why was Fermi's nuclear reactor self-sustaining? We know that in order for it to be self-sustained, it must have a chain reaction in the reactor, i.e., on average, every fission causes another fission. This is very important. Okay, now you can either say that it's self-sustained due to a chain reaction because all you need is just one neutron, and once it is maintained properly, like this overall structure of it, fission reactions keep occurring, and one fission reaction sets off another one and another one, etc. It's self-sustained. You don't need to constantly keep firing neutrons at it. Okay? And if you say either it's due to a chain reaction, or you basically explain what a chain reaction is in words like, for instance, on average every fission causes another fission, you'll get 4 marks. In part 9, we are told that graphite was used in his nuclear reactor, and we are asked what was the purpose of this graphite. The purpose of this graphite, so that it would act as a moderator. This is a well-known fact of graphite. You can also use a moderator as something called hard water as well, or deuterium. And this moderator slows down neutrons, and if neutrons are slowed down, this increases the rate of fission. Moderator's job is to slow down neutrons, and if you slow down the neutrons, it increases the rate of fission. So either one of these 3 options, they are all synonymous with one another, and hence either one will get you 4 marks. In part 10, we are asked, is nuclear fission a spontaneous or a non-spontaneous process? And we're asked to explain our answer. Answering the first question is simple. Nuclear fission is a non-spontaneous process, and you'll get 3 marks for this statement. You'll get another 3 marks for your explanation. It is a non-spontaneous process since a neutron is required to initiate this process. Your explanation will get you 3 marks. If something is required to start a process, it doesn't happen randomly, or it doesn't just happen from thin air, which is basically the definition of a spontaneous process. So with this reasoning, if something is needed in order to set off this reaction, it's non-spontaneous. And that completes question 10A. Okay, so part A is done and dusted. Now moving on to part B of question 10, which will be of interest to you if you study applied physics. So at the start, we are told that a moving coil galvanometer detects and measures small currents. This bit of information leads us on to parts 1, 2, and 3 of question 10, part B. And in part 1, we are asked to describe, with the aid of a labeled diagram, the principle of operation of this galvanometer. Okay, so it says that we're to describe this operation of the galvanometer with the aid of a label diagram. So I'm going to start off with the diagram, bearing in mind that you must label it. If you do not, you will lose marks, okay? Because the labels will tell whoever is reading it a lot of what is actually going on in the experiment or the description you're giving. Okay, so here is the diagram, and I've labeled all the key points of the diagram, which will get you your marks in this question. So you're going to get 3 marks for the overall diagram in this question, but that's only if you have, say, the scale and the pointer. Okay, so the pointer points to the measurement on the scales, which is measured in milliamps, and even though it's not explicitly stated in the marking scheme, I would always encourage you to put on your galvanometer whatever units it's measuring. In this case, it's going to be the milliamps. You can measure this in amps or microamps or anything like that. But just as long as you put a unit there, it gives you a little bit of perspective in the exam. You also must include the coil spring, the moving coil, the soft iron cylindrical core, and the magnets. They're all very key components to the galvanometer, and including all of this, you'll get your 3 marks. Okay, so your coil, core, magnets, and spring, all of these labels are all important for its principle of operation, which I'm going to explain down here in my little description as I have up here. Okay, so the operation of this moving coil galvanometer is based off of the principle that a current carrying conductor in a magnetic field experiences a force. And therefore, when a current passes through the coil, there are forces on the sides of the coil. And then these forces cause the coil to rotate. Looking at our moments of force, our torques here, is the rotational equivalent of our linear forces. Now, where do you get your remaining 6 marks? You'll get the first 3 from stating that a current must pass through the coil. And your other 3 marks will come from that the coil experiences a force, and these forces cause the coil to rotate, giving you 3 marks, giving you 9 out of 9 for this description. Okay, so now in part 2, we're asked to draw label diagrams to show how a moving coil galvanometer can be converted into A, an ammeter, and B, an ohmmeter. Now we know that an ammeter measures current and an ohmmeter measures resistance, but we're going to focus on part A. And remember, again, key point here, you need to label your diagrams. You will lose marks. Okay, so first of all, looking at part A, which I've dictated over here, and you should label all of your diagrams very, very clearly in the exam so that the examiner knows which party you're talking about, because if you label this by mistake as part B, you will not get any marks because it would be a misunderstanding of the general question, and it would not show your understanding of your galvanometers, of course. So this is part A, showing how a galvanometer can be converted into an ammeter. And the setup is as follows. We have a low resistance, or what's called a shunt, and that must be in parallel with the galvanometer. Now, I have the circuit symbols for the galvanometer and both the shunt here, or the low resistance, in my diagram. I've also labeled them because, again, I want to exaggerate my point that these diagrams must be labeled. However, you do not need to learn these circuit symbols off by heart. If you go to pages 72 all the way to page 78 in the Formula and Tables book, these 6 pages give all of the circuit symbols you will need in this exam. So please do not learn off any circuit symbols. Use those 6 pages very, very carefully. Okay, so how does this work? So we have the current going into the circuit, as I've dictated over here. And then a small amount of current goes to the galvanometer, because this arrow is a lot smaller than this arrow. And a large amount of the current goes to the low resistance, because in comparison, the galvanometer has a very, very high resistance in comparison with this shunt. Again, low resistance. And we know the value of this resistor chosen. Okay, so the current then flows through the galvanometer, and a known fraction of the current flows through it. We know this fraction, and therefore, if we know the fraction of current going through the galvanometer, we know the fraction of it going through the shunt, and therefore we know the overall value of the current. After that, where do you get your marks? You get 3 marks for including the low resistance, or the shunt, and you get another 3 marks for having it in parallel with the galvanometer. Now for part B, where we are asked the same question, how can it be converted, but this time to an ohmmeter. Okay, so you notice here that the variable resistor I have over here, it is in series with the galvanometer, and so is this power supply here. So we need to include the power supply and the variable resistor to get our first 3 marks, and your other 3 marks for showing that these elements of the circuit are all in series with one another. Okay, so brief explanation. If we have that A and B are connected, then obviously the resistance between them is nil. It's nothing. Now, we're going to choose this R value of the variable resistor so that the galvanometer gives what's called full scale deflection. But if we take A and B apart and we put a conductor in, we know that the resistance shoots up, it increases. And therefore, the size of the current flowing is thereby reduced, and it can be measured on the galvanometer scale. Now, the position of the pointer, as we saw in part 1 of this question 10b, indicates resistance value, and therefore we can calibrate it to read resistance directly, and therefore you've turned your galvanometer into an ohmmeter. Now moving on to part 3, this is a calculations part of our question 10b, and we are told that this moving coil galvanometer has a full scale deflection. Okay, so before moving on to part 3, I want to draw your attention to pages 61 of the Forming Tables book, in which we will be looking at the resistance formula, or is equal to V over I, also known as Ohm's law. Okay, so looking at part 3, it's calculations part in our question, and we are told that a moving coil galvanometer has a full scale deflection of 50 milliamps, an internal resistance of 7.2 ohms. We are asked to calculate the resistance required to convert it to a voltmeter. This is a very important point because it will dictate how we are going to calculate this resistance and also how we need to set up our circuit. But this voltmeter must have a full scale deflection of 10 volts. Now, before I begin any calculation in physics whatsoever, I need to draw some sort of diagram to try and visualize what the numbers are going to tell me. What do I actually need to calculate, and how do I do that? Diagrams are really, really useful, really, really important, and it really can help you iron out any mistakes that you might make in the exam, and it can really make your head clear when you're going through a calculation. And it also is considered a form of rough work in the exam or any of your calculations, so you can even pick up marks along the way in some questions. And the diagram in this question is as follows. We have a resistor here in series with our galvanometer, which has an internal resistance of 7.2 ohms, and we have a current flowing through it. Well, we need to have a full scale deflection current flowing through it of 50 milliamps. We don't know what this resistance is, denoted by or, we're going to have to find that out. But overall, we have this voltmeter set up here because we've converted the galvanometer to a voltmeter setup here, but we need to have a full scale deflection of 10 volts. Okay, so how do we do that? Well, we first of all must realize that full scale deflection actually means if we have that when 10 volts are put across this combination here, the galvanometer must give a full scale deflection of 50 milliamps. Again, as I said earlier, 50 milliamps must flow through the circuit. This is basically what it means. So first of all, we need to start off that the potential difference across the resistor, or which is also called the multiplier resistance if we're converting this galvanometer into a voltmeter, plus the potential difference across this galvanometer, which has an internal resistance of 7.2 ohms, must equal the total full-scale deflection potential difference of 10 volts. You can either interpret this as the resistance of the multiplier plus the internal resistance of the galvanometer must equal the total resistance in this circuit setup. And both of these points come from the fact that if we have these elements in series, we add the resistance and the potential differences directly. It would be different, as we know, if they were all in parallel. Either stating the first line or the second line, you'll get your first 3 marks. Now, we know that the current going through both the resistor and the galvanometer are the same, and therefore by using Ohm's law, which you can see over here, or is equal to V over I, where V is the potential difference, I is the current, or is the resistance. And we're going to put this in a more useful form, namely, the potential difference is equal to the resistance times the current. And why? It can be clearly seen that we need to put it in this form when you look at our first equation up here, since we need to convert the resistances we were given in the question, along with the currents, into potential differences. This is what we are looking at in this equation. So the potential difference across the multiplier, or this resistance we need to calculate, is just going to be or times the current, which is 50 milliamps, which is also 0.05 amps. And you can see that I have put that in the diagram on the first page. Now we need to add this to the potential difference across the internal resistance of 7.2 ohms in this galvanometer, which is 7.2 ohms times 0.05 amps, and this is all equal to 10 volts. Now taking out our calculator, 7.2 times 0.05 is just going to give us a potential difference across the galvanometer of 0.36 volts. And this is again all equal to 10 volts, or the total potential difference across this setup. Taking 0.36 away from both sides, we get that 0.05 or is equal to 9.64 volts. Okay, now we're going to have to divide both sides by 0.05 to just get the equivalent of 1 or, which is the resistance of the multiplier. So we have 9.64 over 0.05, hit that equal sign, and we get 192.8 ohms, which here I'm going to round to 193. Giving it to 3 significant figures, or rounding it up to the nearest whole number, is completely acceptable, as long as, of course, you do not forget your units. You'll get 3 marks, again, for this statement of Ohm's law here. You can copy it directly from the Form and Tables book and you'll get 3 marks. And of course, you're going to get 3 marks for your final answer, giving you 9 out of 9 for this calculations question. Okay, so just going briefly back to our question 10b, we are told, which leads us into parts 4, 5, 6, and 7 of this question, that LEDs can also indicate the flow of current. But before we answer part 4, I just want to draw your attention to pages 75 in the Form and Tables book, in particular to the circuit symbol for the light emitting diode, or the LED. And then simply in part 4, we are asked, what is an LED? Now we're simply just asked for it, and since it's given in initials form, all we need to do is just state what these initials mean. The reason why I mentioned that page 75 of your Form and Tables book is that it actually gives you the answer. You know, so that's why it's really, really important to know your Form and Tables book so well, because it can just give you the answers to the question, really. Because it has in the Form and Tables book the circuit symbol for an LED plus what it actually means. And the initials for LED stand for the light emitting diode. Just this explanation will get you 3 marks. Now moving on to part 5, we're asked to describe, with the aid of a label diagram, the principle of operation of an LED. Okay, so I'm going to start again, like I always do, with the diagram first. And here we have it. Now, there's a lot going on, but there's a very good reason to. I like to keep my diagrams super detailed because I prefer to describe how something works in physics with pictures rather than a detailed text explanation. But just to really spell out what's going on here, we have that the LED is it's just a PN junction in forward bias here. Specifically that we have the N junction with the anode and the P junction connected to the cathode here. And I've indicated the flow of current, which is very important if you're doing any sort of electricity diagram there at all. And we have the important aspects of this diagram include the depletion layer and also the actual PN junction here. Okay, so for these 2 features of the diagram, you're going to get 3 marks. Okay, so what's actually going on in this diagram here? Well, let's cut to the description. So when this light emitting diode is forward biased, as we saw in the diagram, the N region, or the N-type region, electrons cross the junction of the depletion layer and they recombine with the holes in the P junction. Now, since the electrons are now at a higher energy after this recombination, they return back to their original position in the N region, okay? Because if they have a higher energy, they are more unstable and they want to return back to a stable state. However, while returning, these recombining electrons, as they make their way to the N region, give away this excess bit of energy as light, and thus the LED emits photons. So where are you going to get your next 6 marks? You're going to get 3 marks for stating that the LED is forward bias connection and that the electrons and the holes interact. Really, so these 2 points. That will get you 3 marks. And you'll get your final 3 marks for saying that this interaction results in the LED emitting photons or emitting light. Either or, it doesn't really matter. And that will get you final 3 marks, giving you 9 out of 9 for part 5. Now in part 6, we're told that LEDs are fragile and we're asked how can they be protected in a circuit. So just a simple answer will do, and we know that a resistor would be normally connected in series with the LED to prevent large currents flowing, which could damage the diode because it would have a surge of current, an overflow of current, and therefore it would be damaged. So 2 points of important information. You need to mention the resistor. That will get you your first 3 marks. And you need to mention it must also be connected in series for your next 3 marks, giving you 6 out of 6. Now let's move on to part 7, our final part in this question, and we're asked to state 2 differences between LEDs and photodiodes. Okay, so I have 2 differences here. I put them both on the screen because I want to just note how I've structured my answer. Make it clear. Your first difference is difference 1. Your second difference is difference 2. So that it's just not all just a big clump of text. Kind of make it in bullet points. Make it clear that, okay, I recognize this feature is a difference, and then this feature is another difference between LEDs and photodiodes. Now, my first difference is that LEDs emit light, whereas photodiodes need to absorb light in order for a current to flow. And the size of this current is proportional to the intensity of the light shone on this photodiode here. Now, for my difference 2, LEDs are in forward bias, whereas photodiodes are in reverse bias. Okay, so they're the 2 key differences here. And you'll get 4 marks for your first correct difference and another 4 marks for your second correct difference, giving you 8 out of 8. And we've successfully completed question 10, part B.